Chapter 33, Alternating Current Circuits. We have studied DC or direct current circuits. Now we're going to turn our attention to AC circuits. The first question naturally is, why AC? Why do we want to study alternating current? Well, there are at least two very important reasons. One is, the power grid is actually made of AC. When you plug an electronic device into a power outlet, into a wall outlet, it delivers the electrical current in AC form, not in DC form. And this is simple to understand because, as you learned in the previous chapter when we talked about electric generator, how does one generate electric power out of other forms of energy, such as heat or such as nuclear power, whatever? Well, we use a turbine. Okay, we turn that turbine in the presence of a magnetic field, and then the Faraday's law will then ensure that an EMF will be generated, induced EMF will be generated, and that EMF is naturally a sinusoidal function. It's a sine and cosine function, that is, and that is of course alternating current, not direct current. So that is one important reason. Another reason is that some of the most important applications of electronics, such as how do you receive radio or television signals, okay, requires electromagnetic oscillation. And electromagnetic oscillations can propagate through space in the form of electromagnetic wave, which we'll see later. And electromagnetic oscillations in an electronic circuit can only take place when a current going through the circuit is an alternating current, because oscillation by definition means the current has to go back and forth. Okay, it has reverse directions, back and forth. So it's not a direct current circuit. And therefore, it is important for us to study AC circuits. Now, we have studied so far three common elements in any electronic circuit: the resistor, the inductor, and the capacitor. Okay, what we want to do now is let us first isolate each of these elements out. So we want to study the behavior of each of these elements alone in an AC circuit. The first is, of course, the resistor, the simplest of the three. We have here a very simple AC circuit. By the way, this is the symbol of an EMF delivering an alternating current. Okay, when you see something that looks like a sine function, that means this EMF is not DC, it is AC. Okay, so it produces an EMF that itself varies back and forth. Now, in particular, let's say the EMF assumed the sinusoidal form V, which is produced by this EMF, has a magnitude of Vm, and it's got an angular frequency of omega, so it varies as a function of time as V maximum times sine omega t. Okay, we know if we hook up this EMF to the resistor, you will produce a current, right? And that current itself is a function of time. How much is that current equal to? Well, obviously, that current would be equal to, according to Ohm's law, Vt over R, right? And I can write this as V maximum over R, then sine omega t. So you see, this is a very simple behavior. You will produce an alternating current due to an alternating EMF, and the current that you produce is proportional in magnitude to the magnitude of the EMF Vm. Okay, in other words, the maximum current Im is Vm over R, is proportional to Vm, and it has the same frequency, same angular frequency as the EMF. It also has the same phase angle. Okay, if you see, this is a sine function, this is also the same sine function. There is no phase difference between these two functions. Okay, so this is the simplest case. When you put a resistor in a AC circuit, a single resistor, nothing else, you'll get a current that has the same exact frequency and the same exact phase as the EMF that powers it. Now, this is how we plot the current and the voltage of the EMF, both as functions of time. Okay, as you can see here, if the voltage is this red colored curve, okay, it's a sine function, is like this, and the current is also the same sine function, just with a different amplitude. The amplitude is V maximum over R, and that is I maximum. Okay, they have the same phase, right? This is something we want to emphasize. So Vm equals R times Im. That is how we find the maximum amplitude of the current if it's a purely resistive circuit. So this is not very surprising. Now, let's look at something more interesting. Okay, let's look at what happens when you put an inductor. You throw an inductor into an AC circuit. So we have an inductor, and we again power it with an EMF, just like the one we had before, with V equals V maximum sine omega t. Okay, now you will produce a current running through the inductor. V is the EMF delivered by the power source. It equals VL, which is L dIL dt. IL is the current going through the inductor. Okay, going through the inductor. Now, if VL equals Vm sine omega t, that's what we assume, right? It's the same EMF as the one that we studied before, the pure resistive circuit. Then what is IL equal to? Well, all you have to do really is to move dt to the other side and then integrate both sides. Okay, so IL, the resulting current, is 1 over L and then VL dt. Okay, VL is a sine function, right? So when you integrate, you get a negative cosine function. Okay, a negative cosine function. Now, the thing about a negative cosine function is I can rewrite this. Okay, I can rewrite a negative cosine omega t as sine of omega t minus pi over 2. Can you see that? Okay, can you see that? Because negative cosine omega t, first of all, it is negative sine of omega t, sine of pi over 2 minus omega t, right? I first change cosine to sine, right? And then, since this is a sine function, it's an odd function. Like when I move this negative sign in, I would just get I can absorb that negative sign, so it's sine of omega t minus pi over 2, right? See, that's what you have here. Okay, that's what you have here. So I get something new. I found that first of all, the amplitude of the current going through the inductor is proportional to the amplitude of the EMF. That's understandable, but it's also has to do with omega now. Okay, it also has to do with omega. The amplitude of the current depends not only on V maximum, but also it is inversely proportional to omega and inversely proportional to L. Okay, a high frequency signal will give you a smaller amplitude of the current. Now that makes totally qualitative sense, because a high frequency signal, it goes back and forth so quickly that overall di dt is larger, and therefore there is greater EMF to overcome. Okay, there is greater EMF to overcome because the EMF induced on the inductor is proportional to di dt. So when omega is very large, you have a greater amount of di dt, and therefore that causes the amplitude of current to be smaller. Okay, so that's one thing. But another thing that is even more striking is that the resulting current running through the inductor is not synchronized with the EMF that powers it. Rather, it lags behind the EMF by a phase angle of pi over 2 or 90 degrees. Okay, so in other words, again, the current in an inductor lags behind the voltage across it by 90 degrees. This is something new. Okay, it's something very important that we have to address. But converse, we can also say the voltage across the inductor leads the current going through it by 90 degrees. Okay, now here is a plot. If I draw V, the EMF as a function of time, just like before, okay, it's a sine function. Then you find that current that's produced in the inductor lags behind it by 90 degrees. So it doesn't start from 0. It starts from a negative value. Okay, so it starts from a negative value, and then it goes up and goes down. So it lags behind by 90 degrees. That's something we keep in mind. Now, as far as the amplitude of the current is concerned, the amplitude of the current going through the inductor is V maximum over omega L. You see, you compare that with the amplitude of the current going through a resistive circuit. We just divided by R, right? See here, in this case, I maximum is simply equal to V maximum over R. R is the resistance, but here, in the case of the inductor, we have V maximum over omega L. Now we can think of this omega L as something that's equivalent to the resistance of a resistor. Okay, and we give a symbol for it. We call it X sub L. L standing for the inductor. It's omega times L. But of course, we don't call it the resistance because that confuses with the resistor. We call it the reactance. Okay, or inductive reactance. Okay, inductive reactance. So just like in the case of a resistor, you have I maximum equals V maximum over R. Here you have I maximum equals V maximum over XL. Okay, XL is omega times L. And unlike the resistor, which has nothing to do with frequency, okay, here the reactance increases as omega picks up, and of course it also increases as L increases. Okay, so an inductive circuit, an inductor, is highly sensitive to a high frequency signal, but it allows a low frequency signal to pass with much greater ease. That, of course, is due to Faraday's law of induction. Now, thirdly, let's consider a capacitor, right? So I use the same exact EMF to power a capacitive circuit. Okay, and here you have a capacitor. This EMF, of course, produces a current, an alternating current going through the capacitor. So VC equals this V here, and it's Q over C, right? Q over C. And Q is I dt. So the current going through the inductor, going through the capacitor is I sub C. Okay, IC. IC is dQ dt, and it's ddt of C VC, right? Because Q equals CV. And VC, the voltage across the capacitor, equals that V over the produced by the EMF. So it's just C times V. Okay. Now V is just like before, V maximum sine omega t, right? So you take a derivative, you get cosine omega t, right? The current goes like cosine omega t, which can be written as sine omega t plus half pi. So you see, this time the current leads the voltage across the capacitor by 90 degrees. It doesn't lag behind by 90 degrees, it leads by 90 degrees. In other words, the voltage across the capacitor lags behind the current by 90 degrees. Okay? So again, if you think of the voltage across the three elements R, L, C as the same, the resulting current will have different phases. Okay, for the resistor, it has the same exact phase as the EMF. Okay, for the inductor, the current lags behind the EMF by 90 degrees, but for a capacitor, it leads the EMF by 90 degrees. Okay, and just as the case of inductor, I can relate the amplitude of the EMF with the amplitude of the resulting current running through a capacitor. I maximum equals omega C times V maximum, as you can see here, omega C times V maximum. Okay, and V maximum therefore is 1 over omega C times I maximum. But just like the case of inductor, I can define V maximum as some sort of reactance times I maximum, and this reactance, it is the capacitive reactance, of course, is equivalent to the resistance R in a purely resistive circuit. It is V equals IR. Okay, and you notice that the capacitive reactance, okay, XC, capacitive reactance, is given by 1 over omega C. It is not omega times L or omega times C. It is 1 over omega C. So what does that tell you? It tells you that the greater the frequency, the higher the frequency of the current going back and forth, the lower the reactance, which means the greater the current will get. Okay. Now that means the capacitor behaves just the opposite as the inductor. The inductor will permit low frequency signals to pass through easily. Okay, it tries to block out high frequency signals because it has a very large reactance. Okay, and the capacitor, on the other hand, allows high frequency signal to pass with great ease, and it blocks lower frequency signal. And that makes sense because if the frequency is very high, if everything is the same, the frequency is very high, that means, you know, the current can only run in one direction for a very short period of time before it has to reverse. So there is not enough time to accumulate a lot of charge one way or another. Do you agree? There is simply not enough time for charging and discharging. It happens so rapidly, and therefore you never really build a lot of charge on these plates, and therefore VC would be small, which means you can easily the two plates are never nearly fully charged, and it doesn't take a lot of EMF therefore to overcome the potential difference. You can easily drive a signal through. On the other hand, if omega is small, then it takes a long time to charge it up and then long time to discharge it, and that means there is a lot of time to build a large Q and therefore large VC. So you have to drop a lot of voltage drop across the capacitor, so it becomes just equivalent to a very large resistor. Okay, so again, a capacitive circuit will block off low frequency signal, allowing high frequency signal to pass, and the inductive circuit does just the opposite. And once again, if I plot V as a function time, just as before, it's a sine function. This time the current is a cosine function. Okay, it leads the sine function by 90 degrees. So it starts from maximum and then it starts from maximum and goes down. All right. So this is the so-called capacitive circuit.